Okay, let's get started on the very first step of the process in detail, which is the functional group. Lots of time, the functional group is pretty straightforward to pick out in a molecule. Oh, wrong molecule. Let's try this one first. This is citronellal. You guys have run across it before. If you've ever had lemongrass tea, or your parents have ever made you, oops, a pickle, made you clean the house with Pledge, or if you've used those citronella candles when it's mosquito-y out and you're hoping that maybe it cuts down on the number of bites that you get. This is citronellal. If you were to pick out a functional group on this, I think even if you didn't remember what all the different functional groups are and what they look like, you would probably start right away and say, well, there's this guy here with this oxygen and a double bond to it. That's probably pretty important. And it is. That's a good instinct to have. This is an aldehyde, which means the end of the IUPAC name will be al. It's kind of cool that often the common name will have that as well. Citronelle al is because it's an aldehyde. And we knew that before we gave it the name, therefore, the name. The name itself in an IUPAC fashion would not be citronelle al. It would be a 1, 2, 3, 4, 5, 6, 7, 8, an octene al with a couple extra methyl groups too. But at least you have a good solid state on this is my functional group in the molecule. Alkenes and alkynes are not technically functional groups, though when we get to the parent hydrocarbons video, which is the very next one, you'll see that often they end up acting a bit like they're a functional group, even though they're not. Here's another one. Some of you may have this in your mouth as we speak. This is menthol. Both as the hint in the common name tells you. Oops, that would be better if I gave it the functional group. And I think it's fairly straightforward to say the only thing that isn't a carbon with hydrogens on it is likely to be our functional group. This guy is our alcohol, making it a all, or in this case a cyclohexanol with a couple of alkyl substituents. That's all pretty straightforward. Where it gets a little bit tricky is when you have to choose between more than one functional groups. And to do that, with a molecule like, for example, raspberry ketone, let's see, it's a plant. There's our raspberry ketone there. It has two candidates. It has this guy, which is a carbonyl or carbon double bonded to an oxygen. And on either side of it are carbons, which makes it a ketone. And we also have an alcohol. Now, as we talked about in the first video, there is no two functional groups in a molecule unless they happen to be identical. There can be only one functional group. And the consequence of that rule is that we have to have a ranking system for them. Conveniently, we do. Our ranking system with IUPAC, greatly simplified. There we go. Goes like this. Now again, this is not everything. This is a subset that'll get you started quite easily. It's also the functional groups that I expect you to already know at this point in time. You've seen them in high school. You saw them at the end of first year, last year. You may even know some functional groups that I haven't bothered putting in here, like thiols, for example, or imines get mentioned at least a little bit in first year. But it's a really good starting point, and there's only 3, 6, 9 of them, which makes it pretty straightforward to commit to memory. Organic chemistry is not about memorization, but there are a couple things in it where you pretty much have to memorize things. This is one of those things. Really one of the very few things that you're stuck memorizing in organic chemistry. Highest priority in this list, not in actuality, are carboxylic acids. They walk through esters, acid halides, which are a carbonyl with a halide on the other end of them, amides, nitriles, then aldehydes and ketones, then alcohols and amines. There is a bit of underlying logic to this if you think about electronegativity and number of bonds. But it's pretty hard to sort out. It's easier just to memorize the list as it is. If we're to keep that in mind now, and we look at our raspberry ketone, we can see our two functional groups in here are both on this chart. There is an alcohol, and there is a ketone. Ketones are higher than alcohols on the list, and therefore the functional group is ketone. So the end of our molecule, the end of the name, will be -one. It is a butanone, actually, a phenyl substituted butanone, butane being 4 carbons. So that seems pretty straightforward. And the good news is that it's not a trick. It's generally that straightforward. We can make somewhat more complicated molecules. For example, GABA is fun. This is your brain molecule of happiness. 1, 2, 3. That would be, this is a carboxylic acid. The carbonyls are tricky. When you see a carbonyl, you often want to just flinch to ketone, a carbon double bonded to an oxygen. But there are a lot of functional groups that contain a carbonyl. A carbonyl that has a hydrogen on one side is an aldehyde. A carbonyl that has a halide on one side is an acyl halide. A carbonyl that only has carbons on either side is a ketone. In this one, we have a hydroxyl group on one side, so it's a carboxylic acid. This guy here, nice and straightforward, is an amine. Not all NH2s are amines because it too could have had a carbonyl next to it, making it an amide. But if there's nothing else there, they're amines, nice and safe. Amines are at the bottom of the list. Carboxylic acids, as you may recall, are right at the top of the list. So GABA, which stands for gamma-aminobutyric acid, or butanoic acid, depending on how old you are, the A on that actually tells you the functional group as well. So this is an oic acid. Oh, what's another fun one? Let's get a little bit more complicated, but not a lot. Here's a molecule none of you have ever heard of before, called ecstasy. I think it made it on a TV show once. Or MDMA. Now we got a couple things here are likely candidates. We have our amine. That's an amine right there. And we have these guys. These guys are sneaky for a lot of reasons. People don't tend to see them. And when they see them, they start thinking that they're functional groups. This is where the IUPAC system gets a little bit funny. This is an ether. A diether actually, because there's 2 oxygens surrounded by carbons. Ether and ethers are not functional groups by IUPAC's definition. That doesn't mean that we don't do reactions with them. There are some reactions that we do with them. So that is a bit tricky. The other common example of this, the things that you would figure based on the fact that we do chemistry on them that should be a functional group and are not, are halides. We have, I think it's 4 chapters in the textbook that are basically reactions of alkyl halides, substitution and elimination reactions. So you would figure that it'd have to be a functional group, but halides are also, by IUPAC definition, not a functional group. So they can never be the functional group. The best they can be is there's a functional group in the molecule we can do chemistry on. Keep in mind, I realize I'm repeating myself, but it's important because it's confusing. There is a difference between what IUPAC considers a functional group and where chemistry can happen. IUPAC's goal is very, very simply to come up with a system where an individual name completely describes what a molecule is, and that no 2 different molecules will ever have the same names. So their rules for figuring out what is and what isn't a functional group are based as much on that as they are on basic chemistry. Okay, let's take some more complicated molecules so that you get a little practice with that. The ones I'd like to pick for this are a drug and its antidote. The opioid crisis has been big in the news lately, quite big in the news lately. Phenetyl is the one that gets talked about quite a bit, but the one that we're going to do now is the next generation down the line. The direct opioids were the first generation, like morphine. The second generation is things like phenetyl. And then the third generation are molecules like the one that I'm drawing now, which is carfentanil. Phenetyl itself is 100 times more effective or potent, I guess would be a more polite term for it, than morphine is. And this guy is 100 times more potent than phenetyl is, which is remarkable because phenetyl, starting off with, morphine is extremely potent. It is a plant natural product. It's been known about for a very long time. We all know, I believe, that it is highly addictive, but it is also an extraordinarily effective painkiller. It is a drug of abuse, as we know phenetyl is as well, and as carfentanil has been increasingly found to be. Its original sort of medicinal use is for big game tranquilizer darts, and the rules for using it are extremely strict. You have to use it in pairs. So that there's somebody else there. The person that isn't carrying the tranquilizer gun is required to have 2 doses of the antidote in their pocket. You have to wear protective gear, and there are stories abounding of it ending up in somebody's leg instead of in the animal that you were shooting for. Anyhow, pretty dangerous stuff, as highly effective medications often are. The first reports of abuse of it were around 2016, and it has spun dramatically from there. Now, we have a molecule here with several candidates for functional groups, and they're ones of the tricky ones, which is why I picked it. We have a hidden amine. This guy here is an amine. Amines only have carbons and nitrogens off them. Sorry, carbons and hydrogens off them. So we are safe here. There's no hydrogens on this nitrogen, but there are just 3 carbons off of it. And none of the carbons are carbonyls. We have this guy here. At first glance, you might say, hey, look, a ketone. You'd be sort of right, because a lot of times when people say ketone, what they meant to say was carbonyl. Carbonyl is a carbon double bonded to an oxygen. However, this carbon double bonded to an oxygen is also attached to another oxygen. That makes it an ether if that oxygen doesn't have a hydrogen on it. It makes it an acid if there's a hydrogen on it. But this dash here implies that there's a methyl group, not another hydrogen off of it. So this is an ester. Tricky functional group number 2. Once again, we have a carbonyl. There's a reason why we're focusing on carbonyls. A lot of the second term's chemistry is carbonyl chemistry. This carbonyl has a nitrogen off of it. So no, it's not a ketone, it's not an aldehyde, it's not an ester. If it has a nitrogen off it, it's an amide or amide. That's a Canada English pronunciation difference. Oh, and I don't care how you say it. So there we have amines, esters, and amides or amides. So we go to our trusty list. There's the ester. There's the amide. There's the amine. The highest on the list in this case is Lester the ester. Lester the ester wins the game. This molecule is technically an ester. Pardon me while I hang that up. Okay, now the next guy you guys can actually get on campus to carry around as a kit. It actually shares very much the structure of morphine and codeine and all the other opioid derivatives. This 3-ring structure here with the top phenolic, and then this totally awesome bridged nitrogen ring. That's over the top of the molecule, and in this case it has an allyl chain, which is not present in morphine itself. But this guy is Narcan, or as we call it in Canada, naloxone, which blocks the binding of the opioids. And as you know, I believe, because it's in the news all the time, it's like pure freaking magic when you inject it in somebody who is semi-comatose from opioid overdose. And like magic, they're restored to near normality. It also has a number of possible functional groups. There's our sneaky nitrogen again. We have an alcohol. Oh, so that's an amine. We have an alcohol. We have another alcohol, which would cause us problems if it ends up winning. We have a ketone. For the record, ketones don't have Y's in them. And we have this ether ring here, which, as we talked about earlier, is not a functional group. If we look at our list, amines are at the bottom, alcohols are, right above that, and ketones are just above that. Come on, list. Amines are at the bottom, alcohols are just above that, ketones are just above that. This guy wins as a ketone. And the end of its name would be -one. You may have noticed I didn't tell you the end of the name of ester, because we're going to treat esters in more detail in the substituents chapter, or substituents video, which is 2 videos after this one. Esters are a little bit tricky to name, but not once you know the trick. Amides and amines are also a little bit tricky to name. And we'll deal with all of them together because it's the same set of rules. So that's it for functional groups. Step 1, your job is purely to figure out what is the highest priority functional group in the molecule. Keep in mind, we have molecules that don't have functional groups. That's not the end of the world. We can still name them. They're actually quite tricky, as I'm sure you remember from high school, because for some reason they spend a long time on naming of alkanes. We will not. But we will look at some simple examples of, for example, alkyl halides and ethers, where there is no functional group in the molecule, and you have to use start with rule number 2 or step number 2 of determining the parent hydrocarbon. But here, if there is a functional group that's on our list, it's quite straightforward to figure out. Look for the things that kind of collect heteroatoms and start figuring out if they're going to be your primary functional group for the molecule. That's it for now. Our next video is the parent hydrocarbon, which often depends on step number 1, except for when it doesn't, like we just talked about. It is also fairly straightforward. Our first really complicated step will be the substituent step, which is the 2 videos from this one, or the 3rd step. I will see you all later.